Hello, everybody. Today we have a special seminar, a breaking news seminar, with our speaker, Dr. David Jones, who will talk about his latest paper published in Nature this week. In this paper, they report the discovery of a Supernova Type Ia progenitor at the heart of a planetary nebula. David obtained his PhD at the university's Jodrell Bank Observatory in Manchester. During his PhD, he spent 1 year in La Palma working as a support astronomer for the ENT. He then moved to Chile to take up an ESO fellowship, working with the FORCE 2 instrument at the Paranal Observatory. In his fourth year of the fellowship, he had the opportunity to move to the Universidad de Atacama in the north of Chile to help found their new astronomy department and do some teaching. At the end of last year, he moved back to La Palma, and he's now working with Romano Corradi at the IAC. Thank you.
Thanks. So I'm going to talk today about the paper of ours that came out in Nature on Monday. That was led by Miguel Santander, who was a PhD student here, about the discovery of a super-Chandrasekhar double-degenerate binary in the heart of this planetary nebula, Hennis 2428. So I'm going to mainly talk about why we were looking there in the first place, and not so much about the implications for supernovae type Ia. That's for other people that are more involved in supernovae type Ia. So first, we need to talk about planetary nebulae, and I hope it doesn't matter that some of my slides are in Spanish, because I stole them from a talk that I gave in Chile. So there will be a mix of Spanish and English, but I'm going to assume that everyone can understand. So what is a planetary nebula? It's a shell of gas around an evolved star, a post-AGB star, made from the mass that was ejected by the star while it was on the AGB, or even before that on the RGB, and then has been ionized by the now exposed core, which is on the way to becoming a white dwarf, or on the way to be joining the white dwarf cooling tract. So this is the stereotypical planetary nebula with a nice round, well-defined shell of gas. And in the center, we have this nuclear, which is the white dwarf. And the model that we have for how these things form, that I've already sort of talked about, is that we have this mass which is lost on the AGB. It's quite dense, it's quite slow. And then when the core is now exposed, once all of this outer shell has been lost, we're left with the white dwarf, which was the core of the AGB star. It's now been exposed because we've thrown away all of the outer layers, and that's much hotter. It drives a more tenuous but much faster wind. The two winds interact. They sweep all of the old material up into a shell, which can then be ionized by the central star. So that's why we expect to see this nice round spherical rim, because it's the gas that's been swept up. But then you look at all of the other planetary nebulae. There are about 3,000 in our galaxy, and very few of them have this nice round shape, maybe only 10%. So how can we explain this, these structural differences, particularly things so axisymmetric? We have a single star that's throwing off its outer layers. We assume that the winds are more or less spherical. When we measure the winds of AGB stars, they're more or less spherical. So how, with a spherical wind, two interacting spherical winds, can we form such axisymmetric shapes with jets, with knots? It just doesn't work with this model that we have. But we think we can solve that. People in the past have thought that maybe it's to do with rapid rotation. If you have the AGB star rotating rapidly, maybe the wind is asymmetric. You have more wind, more mass deposited in the rotational axis. And then when you blow the second wind, it's the second more tenuous wind that's supposed to sweep up the first. It's kind of like blowing a balloon, but holding your finger around the middle of the balloon. So you blow up two bubbles, and in the center you're constricting it because there is more mass. But it doesn't work, because if you want to have an AGB star rotating rapidly enough to make that density over contrast around the rotational axis, it has to be rotating close to breakup way before then. So it will never get to that stage. Magnetic fields could work, but to have a strong enough magnetic field to do this kind of shaping, it would never last long enough. The amount of energy required is just not reasonable. You need another source of angular momentum, which is why we come to binary stars. So binary stars can form these things in a number of ways, by helping maintain the magnetic field by driving a dynamo, or my preferred one, with the one that we seem to work on more, is a common envelope evolution. So we need to go through a little bit of binary evolution and common envelope evolution to understand why having two stars instead of one can help us form these axisymmetric shapes. So we start with our model binary, our test case, and we have two stars, both on the main sequence, one more massive than the other. The more massive star evolves faster, reaches the RGB or the AGB, and increases in size. Overplotted on here, the line that you can see encompassing the two stars, that's a gravitational equipotential. It's called the Roche lobe. So at some point, if the two stars are close enough, when the more massive star evolves quicker, reaches the AGB quicker, grows in size, it will fill this Roche lobe, and some of the material from it will then be attracted onto its partner. If that happens fast enough, it's called unstable Roche lobe overflow, the companion star will also grow in size and fill its Roche lobe. So then we end up with two stars, both filling their Roche lobes, surrounded by the material which is overflowing these Roche lobes, and this material is not gravitationally bound to one star or the other. It's bound only to the system. And this is what we call the common envelope, because it's a common envelope of material which surrounds both stars. Then we need to think about what happens afterwards. There we go, the common envelope. So now that they're both buried inside this envelope, and they're still orbiting around one another, and this material is not bound to one star or the other, they start to experience drag forces. So this is looking down on top of the binary as it spins, and you can see where the two binaries are, the two components of the binary. They're the two red dots. Here this is density. And you can see that as they orbit around each other, the drag forces that they experience inside this envelope of material cause the loss of angular momentum, and they end up spiraling in on each other. That's all well and good, but still we haven't found any way to make this mass be lost in an aspherical way. But if we're losing angular momentum from these two stars, that angular momentum has to go somewhere. It goes into the common envelope material. So as these two stars spiral in, the material that surrounds them is thrown out. And because we have to conserve angular momentum, instead of being thrown out spherically, it's thrown out mainly in the orbital plane. So once these two stars have finished spiraling and have ejected all of the envelope, we are left with an overdensity of material in the orbital plane compared to the polar planes. So then when the white dwarf starts to blow its fast wind and to ionize the gas, we have these interacting shells, and it's again, like I said, like putting it forms a waist for the nebula. And you can see that they're now much, much closer in, which is useful, as we'll see later on. So we see this in action. So these are three planetary nebulae, all shown to have binary central stars. And they all have these rings around the waists of the nebulae. And these rings should be the overdensity that's left from the ejection of this common envelope. The other shapes that we saw earlier on are more complicated to form, and they need mass transfer and all kinds of other things, but they're still, we can still form them. So I think this is This is a video of the process. So this is just an artist's interpretation of the idea. So we have the first star, which is now on the AGB, overflowing its Roche lobe. The material falls onto the secondary. The secondary can't thermally adjust, also overflows its Roche lobe, and we end up with the two stars orbiting around each other inside a shell of gas, which is the common envelope, which then gets ejected in the equatorial plane, in the plane of the binary. Then once we start to blow the faster wind, we end up with a bipolar shape, which is the shape that we're trying to explain in the first place, this reloj de arena. So that's good. We have an idea how to form these shapes. Now we need to prove it. The best way to prove it is to find the binaries and show that they match with the morphologies that we see. So there are 3,000 planetary nebulae in our galaxy, more or less. How many binaries do we know at the center of planetary nebulae? After 40 years of work on this, we know about 40. And mainly that is because of the efforts that we've been doing in the last few years, including the example that I'm going to talk about later. So we have to discuss how you find a binary. So they're too far away for you to resolve the two components, because as we've seen, when they leave the common envelope, they're very close together. Their orbital separation has shrunk, so we can't resolve them with a big telescope. We can't see the two components. We have to find them in a more indirect way. So the most popular way, the way that's proved most successful, is through photometric studies. If we do time-resolved photometry, we can sometimes see the influence of the two stars. So this is an example of an idealized case. Say we have in the center our white dwarf, which is very hot, and then outside of it, we have a less evolved star, a main sequence star, so it's much cooler. That's quite possible because in this case, the primary would have been much more massive. It's extended up the AGB, gone through the common envelope, while the secondary star hasn't had time to evolve off of the main sequence, so we can still be left with a main sequence star. In that case, depending on the orbital phase, we will see a different amount of flux. For example, when we see them at conjunction, so what would be eclipsing if I were to turn this so it's in the plane, your line of sight? If we see the main sequence star, which is the bigger star in this model, if we see the bigger star in front of the white dwarf, it's an eclipse, we'll see less flux. The other side, also an eclipse. But then we'll also see variability through the sides because the white dwarf heats the main sequence star. Because the white dwarf is very hot, it might be 100,000 Kelvin. The main sequence star may be 4,000 or 5,000 Kelvin. It will heat one face of the star. So when we can see the side of the main sequence star, which is facing the white dwarf, we will also see more flux. So this is kind of shown in this little model. Here we can see, I'll do it with a pointer. Here we can see on this side, the side which is facing the white dwarf is away from us. So we see the cold red backside or night side of the main sequence star. Then as we go around here, we can see half of the heated face, half of the cool face, which we call the day side and the night side. On this side, we can see almost all of the heated face. So you will see less flux, a little more flux, the maximum flux, and then back to a mix, back to a smaller flux. So if we measure the magnitude of the central star over a period of time, as it goes around this orbit, we'll see a variation in the flux. And this is an example of one of the binaries that we also discovered here in the paper published by Romano Corradi in 2011. And there's the nebula that goes along with it. And you can see that here there are no eclipses, so it's almost exactly like the little model I showed you in the previous slide. Here we are seeing most of the heated face. Here we are seeing almost no of the heated face. And all the way through, and we get this nice, smooth sinusoid from which we can get the period, and we can also try and determine some of the binary parameters. So that's the best method. We have, like I say, we have about 40 binaries inside planetary nebulae now, and some 35, 36 were discovered with this methodology. So, we started a project to try and find more of these binaries. The previous slide shows you one of the results of this search. And rather than selecting at random planetary nebulae to look for binary stars, we tried to pick the best candidates to increase the statistics quicker. So we picked the nebulae that had morphologies that should be typical of a binary interaction. So these hourglass shapes, very elongated, things with jets. And so we looked through all the catalogues of planetary nebulae, and lo and behold, we find this one, which has the perfect shape. It has a sort of ringed waist, which we think is the leftover from the common envelope. It has bipolar lobes, which should be formed by this hourglass type thing. And it has a nice bright central star, so it should be very easy to do this photometric monitoring. So we went away to the Mercator and observed it and discovered that it has a photometric period of 2.1 hours. That's amazing, because that's way shorter than anything else we've ever found before. But there are a few warning signs. So 2.1 hours is very small. If you have a main sequence secondary, you're getting close to it being inside. With being close to being over contact, they should be distorted. And also, as I mentioned before, the normal shape of this reflection effect, we call, is a sinusoid. So if you fit this with a sinusoid, you see that it doesn't fit very well. There's big gaps here, particularly on the decay side of the brightness. And also it doesn't seem to fit particularly well near the peak. And so we were lucky enough to be observing with a very clever cat who someone had left at the Roque, abandoned at the Roque, and Miguel rescued. And Biff knew that that couldn't be the case. It couldn't be that that was the period. It must actually be twice the period. And so we're not seeing this typical reflection effect. We're seeing something different. And we can also tell that that's true, because this is the same observations but folded on a different period. And you can see that the eclipse depth is slightly different. So that's a sign that we're seeing something different. So what can form this shape where instead of having one peak per period, you have two? So I've already pointed out that these are eclipses. So then how do you get the variation between the eclipses? Well, if you have two stars that are very, very close together, even after leaving the common envelope, then their mutual gravity can distort one another. So instead of having nice spherical stars, the stars take on this form, this sort of change to the shape of their Roche lobe. The stars become gravitationally distorted. So when we are looking at the phase 0.25, which is the phase that would have been on the side here in the previous model, the one where it should be halfway up the slope, we see a lot of light because we're seeing a lot more surface area than when we see it at conjunction. So the profile of the stars, if you look along where they join, you see this smaller projection than when they are side by side. So you can imagine if you go around the light curve and it's completely eclipsing, you start off with this, which is a low in the flux. And as they move around, you see more and more and more and more and more flux until they are side by side, and you see a maximum. And then it begins to drop as you see less and less of their surface area, and it goes back to this. And then round the other side, and back to that again. So in a full period, you will see the two stars like this, one maximum, and like that, the second maximum. And the two minima like this. Yes? Please. No, they are. They are. That's one of the one of the things that I will mention later on, that in all of the cases where we can measure the inclination of the binary and the inclination of the nebula, either through the inclination of the ring or through other effects, they match perfectly. This is just this is not a model of the star that we see in this object. This is just an example to show why we see the 2 peaks per period. So, I can fly across this. So yeah, this is the case where the inclination is 90 degrees, so it's completely eclipsing. And also where both stars have the same mass. So it's an idealized case just to show this effect. So the other one where we have the heated face, we call that a reflection effect, and this is a much less common, which is called ellipsoidal modulation. Anyway, so we got that. Now we've constrained the period, because we know that we have 2 peaks per period. We also know that we have 2 stars, or at least one of those stars must be filling its Roche lobe. So we went away with the VLT and then with the GTC to get some radial velocity measurements. And you can see overlaid on this now we have our model, which fits quite well. So this is a model that Miguel performed, which simultaneously models I-band light curves, which we initially got with the Mercator and then refined with the INT, and B-band magnitudes, B-band light curves taken with a 1-meter telescope in South Africa, and this radial velocity curve with the GTC. So the simultaneous modeling of all 3 of those data sets. Here we have the final light curves with much better errors in I-band from the INT and in the B-band from South Africa. And again, the model overlay now, and you can see that it's a much better fit than the sine curve that we saw in the beginning that rang alarm bells. Great, so we discovered a binary. We're very happy, because what we were originally trying to do is just find as many binaries as we could to show that binaries were the causes of these unusual morphologies. But then if you look at the results that come out of this modeling, the parameters of the 2 stars, we see that both stars are equal mass, of the same radii, the same temperature. So they're almost exactly in the same evolutionary state. It can't be that one is a main sequence star and the other is an evolved star, or vice versa. They must both be evolved stars or something more exotic, which we talk about in the paper, but I'm not going to talk about here. It's over contact, which means that both stars are deformed. Both stars are filling their Roche lobe. Both stars have this strange teardrop shape. As has been the case in all of the other examples that we've modeled, the inclination of the binary matches the inclination of the nebula, so we're pretty certain that it is what's doing the shaping, which is good. And the separation is very small. It's less than 2 solar radii. So taking into account that they're quite massive stellar remnants, they're nearly a solar mass, and they're less than 2 solar radii together of separation, you can see that their total mass, they are 2 evolved stars, 2 white dwarfs. Their total mass is above the Chandrasekhar limit, which is the key limit for thermonuclear explosion. And because they are so close, the time that they will take to merge is much less than the Hubble time, 700 million years. So we have a candidate Type Ia supernova progenitor, which was the real exciting thing that we've had out of this, in that there have been pairs of evolved stars, of white dwarfs found together, but never close enough to merge. Or there haven't been sufficient data to be able to refine the parameters of the 2 stars and find whether they really would merge in such a short time. So all of the hypothetical, or all of the modeling that has led people to believe that one of the main pathways to the formation of Type Ia supernovae is the merger of 2 white dwarfs, resulting in a super-Chandrasekhar total mass, was until now only really considered by the models. There was no proof that it was possible. So this is the first example that this can really be the case. And so that meant a Nature paper and press releases all around, including this press release from ESO, which had a really cool video. So we're zooming in very slowly to the nebula. And then into the central stars. And obviously the planetary nebula won't last long enough to see the explosion, because the planetary nebula only lasts 30,000 years, so it's long gone. We now just have the two stars spiraling on each other by the emission of gravitational radiation before merging and possibly forming a Type Ia supernova. So, just for those that are more interested, how do we think that the system has evolved? I showed you this idea of what a common envelope is like when we have two main sequence stars before it begins. So in this system, again, we started with a binary with two main sequence stars, probably of very similar mass. So one evolves just before the other. Very similar mass, so one just leaves the main sequence before the other one. And they are close enough that we do have mass transfer between the two stars. It's almost certainly not a full common envelope, because if we have a full common envelope, the two stars will be too close together and they probably wouldn't survive a second one. So we have some kind of stable mass transfer between the two, either wind, rho slope overflow, or stable rho slope overflow, depending on what you fancy. And after that, we are left with a slightly more massive main sequence star and the white dwarf. Almost immediately afterwards, the companion must leave the main sequence. If it takes a long time, our star will begin to cool down, and then the two stars at the end will not have the same temperature. So almost immediately after the primary, we will say, reaches the white dwarf phase, the secondary must begin to ascend a giant branch, fill its rho slope, and then we have the common envelope that I showed you before. They spiral in very close together and form this double-degenerate binary. This is actually taken from a paper that found another double-degenerate binary in a planetary nebula, but with a much greater separation. And in that case, one star went through its, one star evolved to the white dwarf phase long before the other one. So they were very different stars to begin with, have a very different mass ratio. But this is the only way that we can end up with two stars of the same temperature, so close together, with the same mass. So, what implications does this all have? So, the Chandrasekhar mass is 1.44 solar masses, and the total mass of this system is something more like 1.8. So it's quite a lot more massive than the Chandrasekhar mass. What implications does that have for the use of supernova Type Ia as a standard candle? If we're assuming that all supernova, or a significant fraction of supernova Type Ia form from the merger of white dwarfs, and the post-merger masses, or the amount of fusionable material after the merger, can vary so greatly between the Chandrasekhar mass and up to at least the mass of these binaries. What implications does that have for the explosion physics and their use as a standard candle? Why is this the first one that we found? Fundamentally, it's because it's difficult. I showed you before that the normal way to find our binaries and the normal way to find binaries with evolved stars is where you have a hot star and a cold star, and one heats the other. But here we have two stars that are very similar in temperature, so there's no heating. You don't see that effect. In general, when they are not so close together, this ellipsoidal modulation is a very small effect, because when the stars are much further apart, their distortion from being perfect spheres is very small. So they're very difficult to detect in general. It's very difficult to find pairs of white dwarfs unless they are eclipsing. However, planetary nebulae have proved pretty good. So we have these 40 binary stars in planetary nebulae, and 6 of them are double degenerates, are 2 white dwarfs. That's a pretty high fraction when you consider how difficult they should be to find, that we actually find serendipitously such a high fraction. So if we keep looking in planetary nebulae, I suspect that we will find more double degenerates, and we'll be able to constrain this physics of the formation of close double degenerates, and possibly Supernova Type Ia progenitors. And finally, as I showed you a little bit, as I just touched on in the previous slide, with the history of this system, it will have taken quite a lot of fine-tuning. The masses in the beginning must have been very similar for the masses in the end to be equally similar. They have to have left the main sequence almost one after the other, with very little time in between. So the only system that we have that is a good candidate, Type Ia progenitor, has a very specific set of conditions that will not be met by all or even a significant fraction of the double degenerate binary stars that we find. So is this a special case, or are there enough systems with this kind of fine-tuning to be able to produce more Type Ia supernova progenitors? I think that's it. Yep, thank you.
Thank you, David, for this interesting talk. Is there any question?
Do you have any information whether do you have a helium white dwarf or a CO white dwarf? I mean, did they go through common envelope on the red giant or on the AGB? Do you know?
So this, a priori, I don't think we know, because we don't have enough. But they are definitely strange, because they don't sit on any evolutionary tracks. But maybe that's to be expected if they've just left the common envelope so recently, and they are. So it's such an unusual system anyway that's over contact, definitely not in thermal equilibrium. Maybe that's not unusual. Also, the question there is, on the RGB, how likely is it to survive a common envelope? In that, on the RGB, the outer material is much more bound. The outer layers of the star are much more bound to the core. So if you go into a common envelope, you need to get rid of a lot more energy to be able to eject it, and that might mean that the two merge. So I think this is something for debate. The other possibility that we entertain in the paper as to what these two stars could be is that they are actually naked helium stars, but that fits even less well with models of these things and the parameters that we can find.
I still have the microphone. Do you know the distance? I mean, how well do you know the distance to the system?
The distance is quite well known. It's been measured by a wide variety of means, mainly statistical, but the measured distance fits perfectly with all of the parameters and the magnitudes and everything, so it all kind of hangs together very well.
Could you go back to the flux variation, the final one, the latter?
Okay. This?
No. The one that said 4.2 hours.
Okay.
So how was the cat involved in this?
So, we spent it was a total of 14 nights in the Mercator, and while we were observing there, somebody abandoned the cat at the rocket. And so rather than leave it outside to freeze and to starve, because that's probably the only place on La Palma where a stray cat could freeze and starve, we rescued him and took him in. So every night he spent observing with us. And so I spoke to Miguel this morning, and he agreed with me that all of the credit for this discovery should go to the cat. Absolutely. Absolutely.
And could you just share the cat's insights on flux variation? So there's some features here which you can see. No. There were some features which you could see, and it would be nice to have a physical picture to go with it, but maybe we don't have one. I don't know.
Okay, so I'll try and walk through the light curve if I can. It's quite difficult, but so the inclination is not completely eclipsing. It's only partially eclipsing. If it was completely eclipsing, we'd see much deeper minima here, rather than this sort of semi-sinusoidal variability comes from this ellipsoidal modulation. So at this phase, we are seeing the two stars like that, side by side. So, and because they have this teardrop shape, we see even more flux than if we just saw the two stars like that. So then as the two stars orbit, you see less and less of this projection. Right? Because you have this and you see a lot of surface area, and then you see less and less and less projected surface area. And that is this decay. And then we have the two different minima, which are eclipses. And the reason that we have slightly different eclipse depths is that even though they are exactly the same mass and exactly the same size, one is 1,000 Kelvin hotter than the other one. And that's enough to produce this very slight difference. So then again, once we've gone through the minima, where the two stars are actually like that, it's not a perfect eclipse. It's at something like 68 degrees. Then we start to go back to having the side profile, where we see a lot more surface area and then a lot more flux. So that's the ascent. And obviously, because we go through this, we see both sides of the stars. You see two maxima per period, and the two minima are the eclipses, like that and like that. It's quite difficult to explain a light curve.
No, that's good.
Okay, sorry. Yeah.
Any other question?
How do you estimate the 700 million years to become a progenitor of the supernova?
So that's based on their masses and the separation. That's the time taken to radiate enough gravitational energy to shrink them until the separation is zero. So it's basically general relativity.
Can you estimate the difference between the temperature in the inner part and the outer part of the star? You know what I mean?
So
the part pointed to the center of mass and the other one. Can you estimate the difference in temperature?
Between the center of the star and the surface of the star? Or
the part that is pointing to the other star, or the center of mass, and the part which is pointing to
No, it's the
one
contact
star.
point. And the,
Yeah.
So, no, I don't think so. I think that's really... you might be able to, if you could get really good resolution, time resolution, so maybe with the ELT, maybe you could try and do some kind of Doppler tomography.
I mean, with the model, you can make a model with a Roche-Loff symmetry, and then you can estimate how much is the difference between.
So,
and also taking into account the irradiation of the other star.
that, I don't know. My feeling is that it's not included.
I think this will be a good candidate for gravitational wave detection experiments like this. And concerning the cats now are the more dangerous species in the islands. It's number one now of the species that has been introduced, and they are destroying. Lizards.
This particular cat has now been extracted. It now lives in Madrid, so it's fine. The island is safe again.
Dave, thanks for the talk and congratulations. Is there any evidence, prior evidence, from the nebula that it's harboring the Kinder Surprise egg. In the sense that you could use it for a more targeted search. Like something that would tell you that this nebula not only has a binary, but it has such a massive binary in it.
The short answer is no, because we have so few to choose from. The 40 that we have of all binaries are such a mixed bag that we can't say yet that one has a main sequence binary, that's a much wider binary, that's a double-degenerate binary. There are certain things that seem to be common vaguely between all of the binary planetary nebulae that we find, but so far, it's one of the reasons why we keep doing this, why we keep trying to find more binaries, is so that eventually we'll be able to draw some statistics and say that if you have this feature, be it morphological or this has a whole lot of dust in the center of it. Maybe if you have a very dusty center, that's a sign of something. But right now, the truth is we don't understand anywhere near enough to be able to make these conclusions.
Sorry, I forgot to. Is there any peculiarity in the chemistry of the nebulae? I mean, or in general, on nebulae that have a binary nucleus compared with the rest of the, or this case in particular, is there?
So, for the ones, there's one study published of this, of the chemistry, and it doesn't seem to be particularly special. But then it's not a really in-depth study of the chemistry. As to whether there are some signposts that maybe there are interesting things in the chemistry of these systems compared to planetary nebulae in general, but we don't have enough. We don't have enough data. So it's one of the things I'm working on. I had a big VLT program last year to do the chemistry of all of the southern hemisphere planetary nebulae known to have binary stars. So hopefully by the end of the year I'll be able to tell you.
Any other question? No? Okay, so let's thank again Dr. David. And now there's a scientific coffee at the library if you wish.